Hi, welcome back. This is Calc 2, and Chapter 8 is all about integration. So we'll learn some higher power methods for doing integrals. And we'll begin with integration by parts. Integration by parts is kind of our integral version of doing the product rule. All right. So anyways, where does it come from? How do we get our hands on this thing? I mean, ultimately, it's a formula, right? It's a formula we apply whenever we have a certain type of integral, so derivation. Okay, so first, just recall the product rule. With regards to derivatives. So you have the derivative of a product of two functions, call them u and v, and what we do is leave one function alone, take the derivative of the other, and then vice versa. Okay, so what we did in the differential equations section is one thing we kind of learned is that we can kind of take integrals on both sides of equations. So that's what I'm going to do right here. I'm going to take the integral on both sides with respect to x. So on the right side, I'll have u, the integral of u, and let's rewrite v prime as the derivative of v with respect to x, and then dx. And then likewise here, so I'll go v and then du with respect to x dx. And on the left, the integral of a derivative, you can think of those two operations as kind of inverses of each other. So if you first take the derivative and then integrate it, you kind of get back to where you started. So you just end up with the uv part. And then on the other side, we have a bit of a cancellation. Intuitively, you can just kind of remove these factors, and you're left with u dv plus the integral of v du. Okay. This is kind of our formula, but not quite. What we do is solve for the u dv. Okay, so I'm going to have u dv here all by itself, and then on the other side, I'll have u v minus the integral of v du. Okay, so it doesn't quite look like it's a product rule, but what's going to happen is you'll have one function here for the u, and then usually the dv portion will be some other function. Okay, so it won't just be u dv. The dv will be some formula in terms of x. So the dv will actually be some sort of function times dx. Okay, so you know, typically your integrals, you'll see a product of two functions, and then you can kind of take it apart using this newfound formula here. Okay. So let's just take a look at this first problem in WebAssign, kind of an easy intro problem here, and just see the mechanics of it, if nothing else. Okay, so problem one. We have the integral of x squared ln x dx. So clearly in this problem, at least, you see, all right, there's a product of two things, and it's kind of like an integral version of the product rule, but not really. It's a little more complicated, but yeah, sure. So in order to apply this formula, we kind of need to identify the little bits and pieces. What is u? What is dv? And then from there, we can get our hands on v and then du. Okay, so u, there's got to be kind of an acronym we'll memorize, but you need to put something in the u slot that you know how to take the derivative of, and you need to put something in the dv slot that you know how to integrate. Okay, so as of right now, we don't know how to integrate the ln of x, so that's what I'm going to put in the u spot, because all I really need for my equation is du, which I can get by taking the derivative of the ln of x. The derivative of ln x is 1 over x dx. Okay. So what's left over? Let's see. I've used this portion right here. I'm good. So pretty much everything left over is what's got to be the dv portion. So I'm going to put x squared dx right here. And then to get v, all I have to do is integrate the x squared dx. And of course, the power rule, we just have x cubed over 3. All right. So this is the information you need in order to pull off the substitutions and the formula here that I just boxed in blue. All right, so let's do that, right? So I have U times V, and in the box, I don't really remember the formula. I just kind of remember, okay, it's this times this, and then minus the integral of that times that, okay? So U times V will be x cubed ln x over 3, and then minus the integral of v du, which will be x cubed over 3 times 1 over x. You can factor out the 1/3, and you'll just have x squared, right? X cubed over x is x squared, and then you have dx. And if things go according to plan, you'll have the result. This result will be an integral you can do, right? So this will be x cubed ln x all over 3 minus 1/3 times, now we just do a power rule, so that will be x cubed over 3 and then plus c, and then we can go ahead and integrate that. You get x cubed, not integrate, but simplify, minus x cubed over 9 plus c. Okay. And I didn't use the same numbers as what's in problem 1 there, but it's the same idea, same progress, same process. Okay, so great. It's at the end of the day, it's just going to be kind of a formula you'll apply. You're not going to rederive it, using this stuff every time, but hopefully you see it's just kind of, a product rule type formula. And we use it whenever we have an integral of the product of two functions, and neither is the derivative of the other. So usually you just do a u sub if it's the case that they're kind of related. But you see in problem 1, these two functions are not related with regards to their derivatives. So a u sub ain't going to work. So what do you try? Well, you can do integration by parts. Okay. So our first kind of issue to tackle is this decision procedure here. What is u and what is dv? Okay, and it usually, if you just follow kind of the logic that you need to put something, you need to make u something that you could take the derivative of, and you may need to take dv to be something you take the integral of, that usually works. Okay, and that's the way I learned it. I didn't have some fancy acronym, but if you must, the acronym is LEAT. Okay. And the first one you encounter is going to be your u. Okay, so what is LEAT? LEAT stands for logs, inverse trigs. A is for algebraic, so that would be like polynomials and stuff like that. T is for trig, and then E is for exponential. Okay, so for example, number 1, when we looked at it, we have two functions. One is algebraic, and the other one is a logarithm. So you go to the acronym, and it says the logs come before the algebraics. So your u value is going to be that ln of x. The log came before the algebraic. All right, and in general, that will work, and that will get the job done. So let's maybe take a look at number 3. I'm kind of marking which ones I do in my notes, so when we work in class, I won't do repeats. So anyways, let's look at number 3. And it's kind of the same two functions. You have an algebraic function, the t part, and then you have a logarithmic function, the ln of t plus 4. Okay, all right, so LEAT says that log comes before trig, so you're going to make your u value ln of t plus 4. But honestly, you would have been forced to do that because you wouldn't know how to take the integral of the log of t plus 4, right? We don't quite know how to do that without deferring to some other method. So you're going to make u the ln, and then the dv the t dt portion, and then you can get your hands on the other materials that we need. So you need du, that will just be 1 all over the guts, dt, and then we need to integrate to get to v. So the integral of t is just t squared over 2, and that will be all the information we need. And then again, it's this times this minus the integral of that times that. Okay? So it'll be t squared over 2, or if you'd rather, t squared ln of t plus 4 all over 2 minus the integral of t squared over 2 times 1 over t plus 4. You can factor out 1 over 2. And you have t squared over t plus 4 dt. On that second integral there, I got to do a bit of long division. So I'm going to go t squared divided by t plus 4. So I go t times t is t squared, so I have t squared plus 4t. I'm going to subtract those guys. T squared minus t squared is 0. 0 minus 4t is minus 4t. So what times t is minus 4t? That will be minus 4. So I get minus 4t minus 16, and then I want to subtract those guys, so I'll just get 16. And so my new integrand in that case, well, the first guy is as is t squared ln of t plus 4 over 2. And then minus 1/2 integral. So it always goes kind of this clockwise rotation. T minus 4 plus 16 all over t plus 4. Right? So again, t minus 4 plus 16 all over t plus 4. And all of that is in our integral. Running out of room there. Then we want to integrate. So the integral of that sum is the sum of the integrals. So you could split that into 3 parts there. Don't forget you have this minus 1/2 sitting on the outside of the integral. But anyways, you'll have t squared over 2 minus 4t. And then you may have to do a u sub. Oops, I hit the side of my pen again, so I'm going to have to go through this issue. All right, so there minus 4t. You can do a u sub if you want, but it's 16 ln absolute value t plus 4 at the end of the day. Plus c, and then you really should distribute. Okay. Sometimes you could do repeated integration by parts. So for example, number 5 is where that would come up. So a kind of section this is repeated integration. By parts. So what will happen is you don't quite get something you can integrate after your first by parts, right? So here I have x squared cosine x dx, and I want to let u get my u and dv. So Lie says that algebraic comes before trig, so I'm going to make x squared my u, and then dv will be cosine x dx. Okay, so integrating v is going to be sine x, and then du will be 2x dx. And as usual, it's u times v, so x squared sine x minus the integral of v du. So that will be the integral. You can factor out 2, you get x sine x dx. Okay. So the problem is that second integral is not quite doable yet. You're not going to be able to do that using Calc 1 methods. So what you got to do is by parts again on that integral. Let me make it clear. It's this thing right here I need to do by parts on again. Okay, so again, Lie says algebraic comes before the trig. Integrating on the first row, I get negative cosine x. And then differentiating the second row, the derivative of x is just 1 dx. Okay. So I got x squared sine x minus 2 times So here I go again. I got to rewrite that integral using the box here. So I'll have negative x cosine x minus the integral of v to u. And there'll be minus cosine x times 1 dx. So I can factor out a negative, it'd be plus integral cosine x dx. And then I can finally integrate the cosine x. That's something I got memorized. So I have x squared sine x. You could start distributing the 2 if you wish, plus 2x cosine x. And then the integral of cosine is just sine, so minus 2 sine x. And then plus c. Okay. So you can keep doing it over and over if you want. If you have to do it more than, two times, I advise you to use what's called the tabular method. And I would never put one like this on a test where you would have to remember how this method works. And honestly, you can always use the tabular method, but there's some tweaks you have to worry about, some stuff you have to remember. So just want to put kind of a footnote here. The tabular method basically encodes by parts over and over. Okay, so you'll have this chart with a bunch of derivatives and integrals, and then there's the issue of always distributing a negative. So the table is going to it's going to have the signs that are going in an alternating fashion. Then you're going to have this list of derivatives from the u's. So we'll just put f prime of x. And then you're going to have this list of integrals from the v's. So I'll just put integral. If you want, you can put your own notation. It's not standard. But anyways, for example, over there, problem number 10, you can kind of tell after a while that, all right, I'm going to have to do by parts 3 times in order to get rid of that pesky x cubed. It's like you just look at the exponent on your algebraic term and you know. So for problem 5, it was x squared. You got to do 2 by parts. For number 10, x cubed, you have to do 3 by parts. So what you do instead then is you're going to list the thing that you can take derivatives of, the algebraic portion, and then you just keep taking its derivative until it's 0. So you have 21x squared, and then you have 42x, and then you just have 42, and then of course you have 0. Okay. And then for the third column, you're integrating your dv portions. So that'd be sine x. Integral of sine x is negative cosine x. Integral of negative cosine is negative sine x. The integral of negative sine x is cosine x, and then the integral of cosine is sine. Okay. So it's quick, but you got to remember the whole setup, and then it's not always going to work, right? So if you have to have that case where the derivatives go to 0. Like I said, there are workarounds, but then you have to worry about some other issues, and it's better just to do the standard up. So anyways, the way it works is the first column times the second column, and then you go down 1 row multiplied by the thing in the third column there. So the first term would be negative 7x cubed cosine x. Let me put that back in black. So you get negative 7x cubed cosine x. And yeah, then you just go to the next row, negative 21x squared times negative sine x. So that's going to be plus 21x squared sine x. And then you go to the third, so plus 42x cosine x. And then you go to the last one, so minus 42 sine x. And of course, plus c. So problem 10, you're going to have to pull that on. I don't remember if there's any other ones. I don't think really there were any other repeated by parts. But it's nice if you end up in a in a class where the teacher's always making you do these crazy integrals, just whip out the tabular method. It's quick. It'll get the job done. Okay. So anyways, that's kind of just repeated by parts on steroids. Okay. Sometimes you'll have these functions that don't necessarily kind of go to zero eventually. So if you have two of those in your integral, you kind of have to do what I call looping. Okay. So for instance, number 9, if you keep taking the derivative of e to the x, you just keep getting e to the x over and over. If you keep taking the derivative of sine of x, it kind of goes around in a circle, right? It'll keep going around in a circle until you get back to where you started. So problems like number 9 require additional care, and we could take a look-see. Let me just mark in my notes what I've been kind of doing. So I did this one. Okay, so I call these looping. Okay, so here we go. Let me do the example, this example I found in the book. But it's basically the same thing as number 9, and then we don't have to worry about evaluating as well. So number 9 is a definite integral. This is indefinite. But anyways, Lie tells me I have to do trig before exponential. So my u term is going to be sine 3x, and then my dv is going to be e to the 2x dx. Okay. So du, the derivative of sine, is cosine 3x times 3. And then the integral of e to the 2x, you may need to do a u sub on your integral, but it'll have a factor of 1/2 flying around. So you just end up with e to the 2x over 2 dx. Okay, okay, great. So again, it's always going to be u times v minus the integral of v du. So I have e to the 2x sine of 3x all over 2 minus the integral, and you can factor off the factor of 3/2 e to the 2x cosine 3x. So you see the new integral ain't that much different than the old one, and that's okay. Don't worry about it. Just keep on pushing with another by parts. So again, trig before exponential. And of course, du this time will be negative 3 sine 3x. And the integral of e to the 2x, we already figured that out, will be e to the 2x over 2. And so I have e to the 2x sine 3x all over 2 minus 3/2. And now I'm doing by parts again on this integral. Okay, so that will be e to the 2x cosine 3x all over 2 minus the integral of, so there's a factor of 3/2, and it should be negative, so it's become positive, integral e to the 2x sine 3x. And that should look familiar, because basically that's where we started, right? That integral right there, and yellow, is the same as the integral where we started. Okay, so this is where it's kind of loops around back on itself. So how are we going to deal with this? Well, what we do is just assign that yellow integral a variable and then solve for that variable. Because, I mean, that's what you want to know. You want to know the integral of that thing. You want to know what that thing is. So the variable we choose is the capital letter I. And then on the right-hand side, let's clean it up a little bit. We'll have e to the 2x sine 3x all over 2 minus 3e to the 2x cosine 3x all over 4 plus, well, it'd be minus when you distribute, right? So we get minus 9/4 integral e to, but we want to replace that with an I, right? So we're just going to put a big I there. Minus 9/4 I. And then, of course, there's a constant of integration floating about somewhere. Right, so now we're going to collect the i's on one side, so I add the 9/4 I to both sides. So 1i plus 9/4 I is the same as 4/4 I plus 9/4 I. That'll be 13/4 I equals e to the 2x sine 3x all over 2 minus 3e to the 2x cosine 3x over 4, and then plus c. And then you want to multiply by the reciprocal of 13/4. So you'll end up with 2e to the 2x sine 3x over 13, and then minus the 4's will cancel, and you get 3e to the 2x cosine 3x all over 13 plus c. Okay, so it's kind of a clever way to do an integral, I know, but there it is. Okay, so for the video quiz, I want you to do my problem number 9 there. So the video quiz is number 9 from my homework. And it's the integral from 0 to 6 of e to the x sine x dx. Okay, so that'll be the video quiz for 8.2. Okay, so those are very, very interesting. For the rest, we'll just take a look at some kind of miscellaneous type problems. Let's see how they work. Number 19 looks quite annoying, so let's try that guy. Okay. Or number 11, sorry, it has kind of a weird variable in there. So anyways, I got the integral of 19 sine of the square root of 19x dx. Probably not clear how to start, but you can do a u sub. If you got no clue, just do a u sub on the square root 19x. I rewrite that as square root 19 times the square root of x. Of course, the square root of x is just x to the 1/2, and then go du. So I'll have square root 19 all over 2 times x to the negative 1/2 dx. I can multiply both sides. So this will be 2 all over square root 19 times x to the positive 1/2 dx, right? So what will kind of happen is that we'll end up with a product of two functions, and then we can do the by parts. Okay, so great. So 19 sine of u times dx, which is 2 over root 19, x to the 1/2 dx. We needed everything to be in terms of u. Let's factor out the materials on the inside there. 19 over square root 19, by the way, is just square root 19. And then we have the integral of x to the 1/2. Well, you can go back to the original information in our u substitution and figure out what the heck x to the 1/2 is in terms of u, right? So I can take that box right there in red and solve it for x to the 1/2. So I'll note x to the 1/2 is basically just u all over square root 19, right? So I can rewrite x to the 1/2, this guy right here, as u all over square root 19. And remember, I've already kind of removed the 19 and the 2 over root 19 as 2 root 19. And then we have sine of u du. Root 19s will cancel, and I got 2 integral of u sine u du. And so that's just a by parts. Okay, so I'm going to come over here. I already have kind of u's and v's. I don't want to use u's and v's, so I'm going to use p's and q's now for the by parts. So p, I'll let, from Lie to algebraic before trig, so we'll let that be u. And then dq will be sine of u, okay, du. And then, of course, dp will be du, and then q will be negative cosine of u. And it will be p times q, so I have 2 times negative u cosine u, then minus the integral of q dp, which become plus integral of cosine u du. So that should be relatively painless. I end up with negative 2u cosine u plus 2 sine u plus c, and then you could back sub. So our u value originally, root 19 root x, let's just rewrite that as square root 19x. So I get negative 2 times the square root of 19x times cosine of the square root of 19x plus 2 sine square root of 19x, and then plus c. All right. Oh, number 6 is always a little bit weird. Let's try that one. We'll just do that one and call it quits. So number 6 is a bit weird because it doesn't look like there's a product of two functions. So for these like parts integrals, usually the big red flag is that you'll see a product of two functions, right? I'm just, again, marking in my notes what we've already done. So I knew. Right. Okay. So what is u and what is dv? Well, you can just have your u as arctan, and then let dv be anything else. So the 1 dx, or if you prefer, you could put the 7 dx in there. And then your v will be 7x, and your du 1 over 1 plus x squared. Okay, great. So, as usual, uv is 7x arctan of x minus the integral of v du. So you'll end up with you factoring out a 7, and then you have x all over 1 plus x squared dx. So you do a u sub on that second integral for the denominator, and then you get du is 2x dx. And then dx is du over 2x. Okay, so you get 7x arctan x minus 7 times the integral of x over u times du over 2x. And it looks like we can factor out 1/2. So you get minus 7/2. The x's cancel. Awesome. So you get 1 over u du. And then it should be elementary, my dear Watson. So you get 7x arctan x minus 7/2 ln absolute value of u, back subbing, you get the 1 plus x squared, and then plus c. Okay, so that should do us. Thank you for watching as usual. I will see you next time.